And we directly go on with the big overall topic of AI in healthcare with a keynote being presented by Philipp Koch. Philipp Koch is from Limebit, and he's talking about introduction of MedModels. Philipp is a passionate data scientist and machine learning engineer who is developing or has developed models for customers from all different sectors of industries. Philipp, we are looking a lot forward to your presentation and your considerations regarding MedModels.
Hi, thanks for having me. Very lovely being here. My name is Philipp. I'm a Berlin-based data scientist and founder and head of AI at Limebit. Limebit is a Berlin-based data science agency, especially focused in healthcare and machine learning in healthcare. Today, I would like to speak with you about the potential of machine learning in medical data. And for that, I'd maybe like to start with some bet that I'd like to place with you guys. And this bet is that I bet with you today that within the next 15 years, one of the winners of the Nobel Prize for Medicine will be a computer scientist. As our group is rather small, can I get a hand raise for who might agree with that statement? Who absolutely disagrees with that statement and thinks this is not possible at all? All right, and all the others are quite indifferent then. Maybe I can try and get you to understand where I'm coming from and why I do think that this is might be like a good bet to undertake today. So when speaking about patient data, I speak about some certain type of patient data, which is longitudinal patient data coming either from hospitals or from insurances, for example. For hospitals, it's then EHR data, so it's electronic health records. And for insurances, we call it claims data usually. And so how can you imagine that? So basically, it's like a long chain of events that are happening. So basically, you've got like one patient admitted to a hospital, then he gets some specific diagnosis, then he gets some treatment, then some prescription, whatever. So it's like a big temporal chain of events of some concepts after all. So all of these things, we just bring them together as concepts. So for these hospitals data, they are very, very detailed. So for each and every patient, we do have like very detailed information. We got like the diagnosis, the procedures, the prescriptions, but we also got like the lab results, we got vital data, we got free text notices by medical experts. So we got like a lot of very detailed information, yet this kind of chain breaks as soon as the patient will go to another hospital, because then this kind of data stream is actually stopped, and we cannot really see what happens at other medical experts. So for insurances, on the other hand, for this claims data, we do have very complete data stream. So for the full term, for the full insurance term, we have information about the patient, but usually just about his diagnoses, his procedures that insurance was built for, and the prescriptions maybe. So rather shallow data, yet very complete data. Yet all of it is a chain of events that is happening to a certain patient, and we have this for millions of patients. And with this data, we see a rapidly increasing research interest. So the number of publications really exponentially grows over the last few years, and we see more and more methods from other domains of artificial intelligence and machine learning are applied to this new kind of data. So we see algorithms that work for other data that is now applied to this new kind of data, to this medical data. And we really see that from natural language processing via computer vision up to sequential analysis, we see each and every research field is covered in this domain, so it's really, really broad. Yet I do think that the practical application lags far behind the academic innovative potential. So on the one hand, we got like the academics, we got like the universities who are publishing papers with tremendous and great innovation potential, yet when working with pharmaceutical companies, with health research institutes, with hospitals, insurances, regulation, with research and development, we do see that there's this kind of gap. So the papers are out there, the knowledge is out there, the innovation is out there, but it's not currently really used in, for example, pharmaceutical companies, or just like up to a certain fraction of the potential that could be used. And why is that actually? So from my perspective, it's one of the main reasons is that medical data sets are not freely available. So there's no community, no open source community that could easily play around with that data, developing a kind of open source setup to use actually. So we see this in natural language processing. You see there's language all over, so you can just download the whole Wikipedia corpus or any book from the Gutenberg project or whatever. You'll find enough data to deal with and to build this open source community and these open source assets. You can also do this for computer vision. There's enough images on there, there's enough visual videos, whatever. You can just use this and build perfect computer vision models. But for medical data, there's no such thing available. And that's why I think we see that universities who have access to that kind of data, they do lack, or the practical application lacks towards that potential of innovation because it's just not freely available, which is all understandable because there are surely privacy-related issues. We got high regulatory requirements, which is also absolutely fine because it's a high-risk field. And we got specific new requirements for this health research. So usually it's been biostatisticians who analyze this kind of data, and now we're turning to computer science requirements. And all of these 3 points might come to be the cause that there's this lack between innovation that is available and innovation that is used. Yet I think we see huge potential, especially in some very interesting fields. So there's this field of medical concept embedding, for example, which I'll come to in a minute. There's this field of treatment effect estimation. So basically take 2 groups of patients, one receiving a treatment, another one not receiving a treatment, and just compare them which treatment was better. Or let's say we're talking about machine learning and patient matching. So just methods in order to ensure that these 2 treatment groups are comparable, because usually one is much older, one is much younger, so treatment effect might not be too easy to compare. That's why we use patient matching, which can be supported via machine learning. Or let's talk about synthetic data. So actually we cannot really share medical data, but actually we can use the help of machine learning and synthesize medical data in order to then make it easier shareable, for example, across Europe. We got the whole thing of explainability and causality. So we need to explain why predictive modeling gives a certain prediction on an outcome. So basically I'm just predicting there will be a bleeding or a stroke or a heart failure within a certain time period. So I'll need to explain this actually to a medical expert. So these are some very interesting fields that arise in the future. And I want to speak about one a little bit further, about the idea of medical concept embedding. Medical concept embedding is basically, so what is a medical concept? Medical concept is anything from a prescription or from a procedure or from diagnosis. So all of these are medical concepts. And as I said, medical data consists of a long chain of these events happening, right? So there's this diagnosis, and then this prescription, and then this procedure, and then the patient is healthy again or maybe dies in hospital. So let's take 3 concepts. So the concept of ibuprofen, the concept of paracetamol, and the concept of COVID-19. And for us, it's actually quite easy to understand that 2 of these 3 concepts are very related to each other, while one is quite far apart, right? So ibuprofen and paracetamol are both painkillers, and they are used whenever there's when you have a backache or a headache or whatever, then you use painkillers. And COVID-19 is actually pretty much something different, right? It's not as similar as the other 2. So these 2 are very close to each other, and the other one is far apart. But unfortunately, that's just knowledge that we have. As soon as we pass this to some predictive algorithm and train a neural network on tabular data or on temporal tabular data, telling them, so this patient got ibuprofen and this paracetamol, actually what the machine learning algorithm understands is kind of like that. So that's actually the language of Telugu, like a Southern Indian dialect, which at least I don't speak. And I just want to give you the feeling how the algorithm sees this, right? For the algorithm, everything is equally different. So there's no concept. They're not close to each other. They're not really anyhow similar or dissimilar. They're just all equally different. And that's actually quite a problem when dealing with medical data, because we have certain knowledge about this medical data, but we cannot really pass it to the algorithm. But yes, we can, by, for example, applying knowledge from natural language processing to this medical data. So for the more tech-savvy people among you, you might know the concepts or the ideas of word-to-vec implementations that are basically implementations using at the very core a scriptgram or continuous back of words. And it's basically an idea where you just define a word by its surrounding, right? And so basically we're doing the same here, but just with medical concepts. So we are defining ibuprofen and paracetamol and COVID-19 by the surrounding that are happening. So usually these painkillers are in a surrounding where maybe any pain is nearby or something. And COVID-19 is maybe more related and more closer to other concepts that are maybe any lung disease or something. So basically, we can then try and use these existing methods on medical data in order to find vector representations that are then a continuous space of long vectors, and in these vectors we have encoded the similarity between different concepts. And I think this is absolutely stunning, and you can really do this. It's actually quite easy because the idea is out there, but the practical usage is not out there yet. So we rarely see this for our customers, that they properly use this, because it's actually hard to implement. So whenever you have got to use something like that, you really have to go forward and take this idea, implement it yourself, and then try it. So that's not really good way, especially with these new requirements towards computer science, especially with this whole focus on security and safety when working with medical data. And this medical concept embedding is only like one thing, so there are even more, but I don't have enough time to speak about all of them. So one might be predictive analytics for longitudinal data. So we're having this temporal sequence of chains, this temporal sequence of events, that is event chain, and we cannot just like use it as static data and just predict on that, but we have to like feed it into sequential models in order to properly predict outcomes for specific patients. Or we work with synthetic data, so we want to synthesize a medical data set to share it more easily. Quite hard to deal with that longitudinal character and just keep the temporal dynamic in the data set. Or explainability and causality, so why does really a machine learning algorithm produces a certain outcome or a certain prediction for some patient. And just like as almost one of the last slides, we have tried and thought about how can we actually deal with this? Because most of the customers that are coming to us are actually asking us all the same questions again. So can you implement this? Is this possible? Can we actually do this with medical data in machine learning? And of course we can, but it's actually not very smart to have it like over and over again re-implemented from scratch for each and every customer. So there might be an interesting way to standardize this, and that's why we've started the research project MedModels a few time back. And in MedModels we are building a software engineered package in Python that implements, for example, the treatment effect estimations that are available, patient matching with machine learning, treatment, medical concept embeddings, medical data synthesis, predictive analytics, and explainability and causality, basically in order to be faster when analyzing medical data, in order to be safe when analyzing it, in order to kind of validating it together to just like bring this potential that is there in the university down to the practical applications in pharmaceutical companies, in hospitals, in regulation, or somewhere else. So that's why I'm placing this bet. So within the next 15 years, I'm pretty sure, because like there's this whole shift of concept, that one of the winners of the Nobel Prize for medicine will be a computer scientist. Is there anyone who wasn't very convinced at the beginning, but is now a little bit more convinced? No one, unfortunately. But thanks anyways. Thanks for listening. If you're interested in medical data analysis, then get in touch, and I'm happy to talk to you. Thanks.
Thanks a lot. Do we have any questions from the audience? We do not have yet, so maybe I start with the first question. You talked about regulation too, about regulation specifically relevant for healthcare. So what do you think about the AI Act in healthcare? How does it is going to influence the way companies offer compliance solutions?
You think at the very end, so we actually do not using the full potential of machine learning in medical analysis because the federal agencies need to be sure that the analyses that we are building as a basis for like some publication are very valid. And so this is a pity, because usually we're just like falling back to logistic regression to analyze something, or to just like plain survival analysis, which is okay, but there's more potential to come. So although this way is hard, and although so it might take a while to get to a point where we can really trust complex algorithms that are hard to interpret. I think this is inevitable to go this way and to have more focus on more complex algorithms to analyze medical data.
Mm-hmm. So we're talking about timeline. So what do you think concretely, how is this maturity growing in the next years? What is happening in the next months, next years in this MedModels paradigm?
Yeah. I think there are like some things that might be easier to catch soon. So I think we could start, and should maybe start, with focusing on synthesizing data. Because whenever we have artificial data, then it's way easier to share. We can kind of build and build this open source community that may deal with this data, we can actually quite somewhat easy check if synthetic data is similar to the original data, or if there's like any leakage of data in there. And I think this might be like one of the very first steps to focus on, because then we can accelerate the whole thing, right? And I think one of the later steps might be to have like fully trusted systems that advise medical experts on outcomes or on treatments, and where you can really trust that. I think that might be step 2. So step 1 along that way might be to really focus on synthesizing data.
Mm-hmm. So another question maybe to the ecosystem you presented in the end. So what are your plans there? Who are your partners for the future to elaborate in this timeline for next year?
Yeah, we are actually very, very happy that we have this great board of advisors supporting our MedModels implementation, because we really need this. So on the one hand, we are an agency consisting of these developers and software engineers and machine learning engineers with like a tiny bit of medical background. But we need medical experts that validate our implementations. So we are closely working together with health research institutes, with insurances, with hospitals. And I think whenever we can get this network to grow and to have more partners discussing the needs and the requirements and actually the regulations and the limitations of what we are doing there, then for us that might be a great benefit.
Maybe a question directly linked to your considerations. So it's a very international perspective you presented, as you have an international view and operations. So healthcare is regulated extremely on the local level at some point. So what do you think there? What are the differences between different member states of the European Union, for example, and even globally? And how can this converge at some point, being realistically that it won't converge too much? But what are your perspectives on that?
Yeah. I think we got to share data in a more broader way, so like on a European level, which is not too easy because of privacy-related issues, which is completely understandable. Then again, synthesizing data or finding ways in order to make this data available without facing the privacy issues might be very beneficial for all members in this group then. So we recommend to just like try and find ways, for example, even using machine learning to work closer together on questions like these.
Mm-hmm. Have you discussed this with regulators or politicians?
We have been in some loose discussions. From our timeline, we are rather in the beginning to middle where we are implementing, and we are in close contact, for example, with some certification partners who might advise us on how to go on there. But I think it's still something to do.
Have you experienced different experiences being made when it comes to different member states of the European Union? Like we talk a lot about digitization in Germany in general, healthcare being the fact that Germany is not very mature. Do you have considerations or tips for Germany?
I'm not in that position, but I think when we are working with our pharmaceutical partners, we usually see that all of the databases that we are working on, they're usually not European wide. So all the data that we are analyzing is American data, it's US data, which is easier accessible, and so I'm not in a position to advise there. But it is obvious that there might be this specific thing about European data and, for example, US data.
Mm-hmm. Thank you. We have another question from the audience. Do we have a microphone? It's arriving.
Thank you. I would like to know your opinion about AI in clinical diagnostic, whether it's going to be useful in terms of speed and accuracy.
I think it can be. So I think we do see that there are like patterns that are like in diagnosis that are better performing than regular, for example, tests that we are having in diagnosis. So for example, take like whenever you're any bleeding, you can just like calculate a bleeding score by some Hasbled score, or for any cardiovascular, you calculating Chadwas scores or something. And medical machine learning can be shown to be more precise on giving these kind of predictions, whether there might be a specific risk for certain patients. Yet this should also and always be accompanied by medical experts to interpret this data, right? So we are far away from that position where we can really trust the AI by itself, but I think we should try and see how it can support medical decisions.
I completely agree with you. I'm from the healthcare background, myself the doctor, I'm a physician.
Nice.
So I'm pretty interested how AI can implement in diagnostic, and I have followed up one more question to you. Do you think AI is also going to help in the clinical trials, which is a very concern? and very crucial area in all the pharma industry.
Yeah. We've been involved in some project where we applied machine learning in clinical trials. I think it's 4 seconds, so I think we can elaborate later. But I think there is also potential for application, as long as this is, of course, accompanied by epidemiologists that, of course, like support the whole process. So never leave AI alone in that field, but try and get it involved a little bit.
Good. Thank you very much.
Thank you.
So thanks a lot, Philipp. I think this was very interesting.
Thank you.
I think you are around here for any further questions. So thanks a lot.
Thank you.